Welcome all. I am Dr. Manoranjan Oja, Assistant Professor, Department of Basic Science Chemistry, SR University. Today our topic is solid oxide fuel cell. So we'll discuss the fuel cell, how it works, what is the mechanism of fuel cell, and then solid oxide based fuel cell, how it is works. We'll discuss on that part. So solid oxide fuel cell are a class of electrochemical energy conversions here. This is the energy conversion devices that directly convert the chemical energy of a fuel into a electrical energy with high efficiency and with low environmental impact. So what we are discussing here, we are discussing about the electrochemical energy conversion system. So energy conversion means it is converting a energy in one form to another form. That is the energy conversions. What we are using is through the electrochemical medium. Right, and directly convert the chemical energy it is converting chemical energy of a fuel into electrical energy. So what we'll use, we will use some chemicals. That chemical energy will be there. It will convert to a electrical energy and it will store it. And with high efficiency means efficiency of the compound will be high and low environmental impact. Unlike conventional power generation systems that rely on the combustion are subject to the limitations of the Carnot cycles, means efficiency close to 1, and operates through the electrochemical reaction. Whereas this oxide-based fuel cell, it is through the electrochemical process, not kind of a combustion system. Combustion means through the burning. This normally works in burning. But what we are discussing, that is electrochemical reactions process, allowing for higher efficiencies and cleaner energy productions. Means there will be no carbon particle generations, or there will be no carbon footprint. So it will be much more greener towards the environment. Due to their fuel flexibility, high efficiency, and suitable for both stationary and distributed power generator, this solid oxide fuel cells are considered as a promising technology for the future energy system. We'll discuss here what we are calling for fuel flexibility and high efficiency. And this solid oxide fuel cells typically operate at high temperature, that is ranging from 600 to 1000 degrees centigrade, and used a solid ceramic oxides as a electrolyte. This high operating temperature enables internal fuel reforming and fast reactions kinetics, making solid oxide fuel particularly attractive for combined heat and power applications. So we'll discuss this one as well in the coming slides. So what is actually basic principle that how the fuel cell work? So if you remember, we discussed that fuel cell, it is use some chemicals. That chemical will, through the reaction, that chemical energy will be converted to the electrical energy. So how it will be converted? So these reactions will take place in this sense. One side will be oxidations and reduction process in the solid state fuel cell. So if you see common this broadly in the fuel this fuel cell has a three part, that is called anode, cathode, and electrolyte. If you see in the pictures, you'll get it. So one side is, this is a cathode side, another side is anode side, in between electrolyte is there. So as we are talking about the solid state solid oxide fuel cells, so inside here this solid oxide is there as a electrolyte, and that electrolyte is acting as a separator as well as electrolyte. Both one role this is playing. Separator, why we are saying, because it is separating anode and cathode for direct contact. So that is this that's why it is called separator as well as the electrolyte. So what this electrolyte, what is it is conducting? It is conducting oxygen ion or the oxide ion at high temperature. But this electron transfer between one to two electrode is will be stopped because it is not conducting. So it is not transfer the electrons. Only it will promote the or move the oxide ion. So how it is working? We'll see here. So this we have two sides. One is cathode and another is anode. So what we are doing, we are passing, let's say for anode side, hydrogen gas. So we are injecting hydrogen gas in one side. Then what is the anode material is there in the anode side? What it's do, this hydrogen ions. So this hydrogen ions, it is reacting with oxides. Then it will form the water and two electron. So reductions of the oxidations of the hydrogen takes place. So here in hydrogen it is a zero oxidation state. Here it is plus one oxidation state. So oxidation state is increased. So it is oxidations of hydrogen is taking places. So is anode oxidations of hydrogen is taking places. So what we are fuel we are giving here, chemicals fuel we are giving is a hydrogen, or later on we'll discuss the carbon monoxide. We will consider here hydrogen only. So hydrogen we have supplied from the anode, then it will combine with the oxide ion, then it will make the water. Water will go to the environment or outside from the cell, and electron it will generate. So this side is electron is generating. Now opposite side, cathode side, we are passing the air. In air, O2 will be there, oxygen will be there. Then oxygen will combine with the electron, then reductions of the oxygen will happen, then oxide will form. So this oxidation is 0, here is -2. So 0 to -2, oxidation state is decreasing. So that's what reduction is taking places. So in cathode, reduction is taking places, here is anode, oxidation is taking places. And then electron is moving from anode to cathode. So we are getting from here energy, that is due to the electron flow we are getting the electricity. That's how it is works. So this continuous flow of the ions and the electron produces the direct current, electricity, as long as the fuel cell oxygen is supplied. So when we will supply the air hydrogen, or in this side water, so that time this electron will generate in the anode and it will move to the cathode. Then we will get the electricity. This is the principle how the solid state fuel cell it works. This component of the solid oxide fuel cell, that is first we'll consider the middle one, that is called this electrolyte. So solid material we are using here. So this is called electrolyte. What kind of the compound we are using here is the yttrium stabilized zirconia. This is the material we are using. What is our criteria is that when we will heat it to 600 to 800 degrees centigrade, so it will produce the oxide ion, it will conduct the oxides, and in that high temperature it should be stable. So it must have a ionic conductivity, because this ion should move in this through this compound. Here oxide ion is moving. And negligible electronic conductivity means conductivity of this compound will be less. If this conductivity will come to the picture, then this electron flow can take place, which will combine to this two cathode and anode, crossing will happen. Then this device will burn, or it will be short circuit will happen. So that's why it should not pass the electron, only it should pass the ions. So the electrolyte separates the anode and cathode, allows only the oxygen ion or oxide ion through the passing. So this is the role of the electrolyte. So two role is there. It will pass the oxides or ions with high rate, that is called high ionic conductivity, and also it makes separate between anode and cathode. So electrons should not transfer from one part to another part. Only ions should transfer, or ion movement should happen. So now that is called anode. So anode usually one composite of nickel and yttrium. This yttrium stabilized zirconia is used. Why we are using this? Because in anode oxidation is taking places. So what the reaction it is happening is what oxygen to hydrogen to water is forming. So some kind of a catalyst we need, that this catalyst will facilitate the oxidations of the hydrogen. So for this catalytic activity, for this oxidations, we need some compound, that is here nickel and the TS stabilized zirconia composite is used. That high electrical conductivity for those material cathode and anode will take, there should be electro movement or electron transfer should happen very fastly, and it happened only fastly because of high electrical conductivity. So when we'll talk about the anode and cathode, we will talk about the high electrical conductivity, whereas for electrolyte we want there will be no electrical conductivity, only ionic conductivity. A porous structure is allowed the fuel gas diffusion. So if this structure is fuel, so what if the structure is porous, then this gas will transfer or can move freely into the compound. So then the reactions will happen freely. So that's why we need one porous structure where reactions will be much more faster. So now is the cathode material. We talk about the cathode material generally made of lanthanum strontium magnesium called LSM. So this is one type of the catalyst we are using for cathode. Here in cathode, what is happening? We are using the oxygen and it is reacting with the it is reducing it to the oxide ion. So O2 minus. So oxide ion it is forming. O minus. So in this we need one catalyst. That catalyst will reduce the oxygen to oxide ion. So that is called lanthanum strontium magnetite is used for this purpose. It facilitates the reductions of the oxygen molecule and formation of oxygen ion. Interconnected, this one we'll see later on. The step by step will make the compound. The cell when we are making. So just like a series connections, we will do one by one that connection. So for that interconnecting, we need this individual cell to be connected one by one. That is called stack formation. And that stack electrically and separate the fuel cell and oxidant gases. It must be electrically conductive, chemically stable, and resistant to oxidations. So whatever we are using the connector, for one cell, another cell, another two, let's say 5 cell we have to connect. Then this connector should have the property of this one. So it will be resistance to the oxidation, chemically more stable, and electrically conductive. Otherwise, that electron cannot flow in these connections. So what are the type of the solid oxide fuel cell available? There are two types of the solid oxide fuel cell is available. One is called planar solid oxide fuel cell. What is that meaning? If you see first this figure here, actually how one unit of the solar cell fuel cell it looks like. So we are passing to gases in both end. One there we see that for gas flow, we need some kind of a setup. So for this one we are using like this, that gas will flow in this way. So if you see, that's what the structure is like this. And this is our support, that is called end plate. It is a support. In that support we are attaching to the cathode material or anode material. Right. After that, electrolyte will give, then again electrolyte will give, then again anode and cathode, then separator. So one by one it is step. Now if you see here as well, this is one electrode or one side of the device. It's one by one it is connected, and this is called the stack model. So cells are arranged in a flat plate like this plate, and offer high power density, easier to manufacture and sell. That's this when we are making, what is the advantage of using the planar solid oxide fuel cells. required effective sealing due to the thermal expansion. Means you need to be connected very well because at high temperature this expansion of the materials can happen, so it may collapse or maybe fractures. So that's why we need a sealing, very good sealing due to the thermal expansions. Another is called like a tubular. So these are cylindrical. If you see here, it is a cylindrical type or tubular type of cell. Excellent sealing and thermal cycling behavior, but low power density compared to the planar design. So here, if you use it, then the power density of this material or low will be very low. So what are the gases will pass for this solid oxide fuel cells? There will be different type of the gases can be used. For consider, we are using the one side that is called that reductions will happen, that is called oxidation will happen in the anode. So what are the gases we can use? For hydrogen gas we can use, that is for hydrogen oxidations will happen and will produce the water. So this is where it is green hydrogen is coming. So we can produce a lot of hydrogen, and this hydrogen can be used for the in the fuel cell for energy generations. It is completely environmental benign and there is no carbon footprint. So this is called, that's why it is called the green hydrogen. So we are not producing any carbon in this, that's why it is not impacting anything to the environment. So this is the best way to go with it. Now another gas can be used, that is called natural gas, that is called methane. So in a same way, this methane can be oxidized. So there is different fuel can be used for this solid oxide fuel cell, that is called natural gas. And biogas also can be used. That what is difference between natural gas and biogas is, in biogas that biodegradable products from the bio decompositions will get the gases, that is called biogas. So from degradation of bio things or some kind of any vegetables or some other things from which is bio related or plants decompositions. So for decomposing all those part, when we get the gases, we call the biogas. It may be, sorry, it can be methane or carbon dioxide, or mixture of both. That is called biogas. And methanol also can be used as a fuel in the solid oxide fuel cells. And it is called syngas. Syngas also can be used. This is a combination of hydrogen and carbon monoxide. So hydrogen gas will oxidize to water or hydrogen ion, and carbon monoxide is oxidized to carbon dioxide. And only carbon monoxide also can be used for the as a fuel for the solid oxide fuel cell. If you see here, for using the solid oxide fuel cell, that we have a different kind of a opportunity, or we have a different options that which gas we can use it for our reactions and energy generations purpose. So this is the this is the major advantage of using solid oxide fuel cells. Due to the high operating temperature, and many hydrocarbon fuels can be internally reformed within the solid oxide fuel cell, eliminating the need for external reformer. So these are the advantages of using the solid state fuel cell. Now, what is the advantage of the fuel cell in the terms of the energy efficiency? Up to 60% of electrical efficiency over 85% CHP. So this 60% of electrical efficiency is much more higher than compared to the others. So this is the efficiency or energy efficiency of the solid oxide fuel cell. And also fuel flexibility we have discussed earlier. Now the different kind of a fuel we can use it. And low emissions also means this when we are using this cell in the high temperature of 600 or 800, this negligible amount of nitrogen oxide compounds form or sulfur oxide compound form. So that's why it is much more greener than that of others, because we are not generating any different of the gases, so these are not good to health, so good to our health. So this is one low emissions of this using the solid oxide fuel cell. Quite operational or no moving parts. So here in high temperature only these reactions will happen, and that only oxide transferred from the one side to another side. High quality waste heat suitable for heating or industrial process. So in industrial, for let's say metal refine process or aluminum, steel, or some different from copper, their temperature is heating is very high. For that one, this solid oxide fuel cell will be much more easier to implement. Scalability from smaller resilient system to large power plant. So means it is very easy to make it a large device, from smaller device to a large devices. So these are the advantages of the using the solid oxide fuel cell. But there are also some limitations for this and challenges for the solid oxide fuel cells. There is high operating temperature. So means this devices work at high temperatures, that is called 600 to 800 degrees centigrade. But this catalyst we are using, if that catalyst is not sustainable or cannot sustain at a high temperature, then you cannot use it. So material can be degradations of the materials can happen. So this is one limitation that using the solid oxide fuel cell. Then long startup times. This one problem is that lagging period for this solid oxide fuel cell. It means only starting the cell, it won't work instantly. It takes some time to become active and participate in the reactions. So there is a long startup times. One you have start, it will take time to function. After started to work, then it will continue. So initial time to start the process, it always take the time. So that's why one limitations for this cell is long startup times. High manufacturing cost. So cost of the material to make this setup or the solid oxide fuel cell, its cost is much more higher, because we are using at high temperature of 600 to 800 degree. So setup will be different than the normal way to use it, because there is a lot of very high temperature is there to heat the setup. This is the system. So that's why we need some kind of a apparatus or setup for this high temperature heating. Thermal expansion mismatch between component. So as we are doing in the reactions very high temperature, this some compound may be thermal expansion will happen, means it will expand. So different compound may be response to the high temperature different way. So there will be some mismatch of the expansions of the compounds. So then if it is this mismatch of the expansion of the compound will happen, then there will be some problem with the device architecture, or it will be stable. Some pressure will generate in the system, and it can break the systems. So that's what it is a very big issue. The thermal expansion mismatch of the compound creates the problem, which is a one limitations of need to be improved, which is challenges we face. Durability and lifetime issues under the continuous operations. But this is because this how long we can work. So for this one, some due to the stability issues, so durability is less and lifetime also is less. So this need to be improved. That is the one another challenges. Research is going on to develop intermediate temperatures which can work in the 500 to 700 degrees. Let's say this is called the manufacturing cost or setup or or thermal expansion mismatch need to be can be controlled by lowering the temperature. So if we are able to make a solid oxide fuel cell which works in low temperature, then this problem can be removed or can be addressed. So that's why that we need some setup need to be input something that we will use for solid oxide fuel cell where the temperature will be less. So we can operate in lower temperature. That will be excellent way to go move on. Where it is applicable means where it is being used that applications of solid oxide fuel cell. It is a stationary power generation. As you have seen, this is stack one by one is connected and the size is bigger. So in portable device we can't use this kind of a system. It is always a stationary power generation. Means you cannot move. It will be very big size. It will be connected one by one in the stagger manner. So then it will be used as a stationary power generation. Combined heat and power system. So it can be used for combined heat and power systems. Distributed energy system, from where the energy can be distributed everywhere, like the power stations, backup power supply, also auxiliary power unit for vehicles, industrial and commercial building, we can use it. So solid oxide fuel cells are also being explored for the marine applications and hydrogen economy infrastructures. These are the applications of solid oxide fuel cell. Future prospects. So with increasing demand for the, we need actually that due to the environmental impact. So we are looking for the clean and efficient energy solutions. So clean means carbon footprint will be much more lesser or near to zero, and efficient energy solutions. So efficiency of the device will be much more higher. So these two, if you look, in that case, solid oxide fuel cell technology is expected to play a significant role in near future energy system, because that we are looking for in environment benign or greenish system. So there we can use this because it is not increasing any carbon particles or carbon footprint, and so it will be environment benign and greenish green process. So that's what clean, we say this is a clean energy and efficient energy. So efficiency for this fuel cell is much more higher. So that's what we are looking for, a clean and efficient energy solution. Then one option is to use the solid oxide fuel cell. Advances in material science and cost reductions and durability improvements are accelerating commercializations. So if we can make some compounds, that we use two type of the compounds here, three type of the compounds. One is for electrolyte, one is cathode material, and anode material. Anode and cathode material, these are the catalyst, and where the reactions of oxidation and reduction takes place. And electrolyte used for the transfer of ions, that is electrolyte, it participate. So if we are able to make a very good catalyst for oxidation and reductions, then process of oxidation and reductions will be much more faster and it will be much more efficient. This prospect we can work or think to make advanced materials that we can synthesize or modify the catalyst for the anode as well as for cathode for better performance. Next is the cost reductions. So we can make the device which is lower in cost. Then that will hugely impact for the big scale or applications or making the bigger way. And durability improvements are the accelerating commercializations. Durability means how long it will work. So we are making the devices, but it is very long lasting. So if it is very long lasting, then it has a meaning of commercializations. So long lasting, cost reductions, and better catalyst or materials will give us a very good accelerating means very accelerating prospect of further commercialization in solid oxide fuel cells. Integrations with renewable energy sources and hydrogen production system further enhance the potential of solid oxide fuel cell as a sustainable power technology. Now here what we are talking, let's say for this running for this fuel cell, we need very high temperature, that is called 400, 700, 800 or 800 to 1000 degrees centigrade. Now it will connect this one to renewable energy sources like wind energy or solar energy, then automatically from that solar energy or wind energy can start the systems, and we do not need to have to provide the energy from our outside. So whatever in the from the natural sources, which is renewable energy, from there it can collect and run. So integrations with renewable energy sources which will give a better impact for this solid oxide fuel cell. And hydrogen production system means where hydrogen we are using, let's say for cathode gases, here is anode fuel is hydrogen gas, where reduction oxidation takes place. So it's connected to the hydrogen plant, then this hydrogen directly can come to the fuel cell and produces the and work and to generate the electrical energy. So that's why integrations with hydrogen production system will further enhance the potential of solid oxide fuel cell as a sustainable power technology. So what we have discussed here, we have discussed that what is this solid oxide fuel cell and what is the mechanism, what is the part or component of the system, and how it works, what is the benefit or advantage we get by using this one, and what are the disadvantages as well as for this using the solid oxide fuel cell, and what is the future prospect, means from where we can improve it for better use of or to make the highly efficient device of the solid oxide fuel cell. Okay, thank you. We'll stop here.